Good afternoon, everybody. I'm Greg Latch. I'm with the Emerson Rosemount team and actually look after the, what we call the Emerson Solutions and Systems group as a BDM for that particular portfolio. So we'll be touching on some of those areas as we go through the slide deck. Today we'll be talking about obviously disinfection measurements and the likes for the water industry. We do obviously anything from gas systems as well. When I say gas, as in components of interest in gas composition measurement. We just did a session in that space recently. Let's flick to the next slide. Just to give you a little bit of background on myself, I'm actually an ex-contractor with Melbourne Water. I was with those guys for a number of years. Must have been a hell of an eye-opener, and you do tend to take water for granted until you've actually worked in the industry. So I've been very fortunate actually. I'm one of the more what's the word for it? I suppose interesting career changes that I had for a period of time when I was working with them. The key points up there I think are fairly self-explanatory though. Water obviously it's crucial for the sustaining life. Without it we don't exist. I must admit I do smoke a bit when I do travel. You can actually go to remote locations and get a Coke Easy, a can of water in some, traditionally in the old cases. Now you do get a lot of bottled water. The pressures obviously in the water and retic systems with the growing population globally. I strongly see this as an area for growth, and we've already seen that recently. But I think there'll be more pressure in the lights in that space, not just from, I like to call it a, excuse me, a rainwater capture aspect and runoff, but also obviously in reuse for wastewater and the likes. And really, definitely one of the challenges for the water authorities is obviously to manage that resource efficiently, obviously in a cost-effective way. Hell of a lot of pressure on the guys and the girls that are in that industry and team, and obviously falling and keeping within the guidelines for their reticulation systems. The agenda today, I think we've pretty much covered it. There's a bit of an introduction and the likes. We will touch on the introduction for disinfection as well. We'll talk about chlorine, chloramination, a little bit on sensor technologies and system solutions currently available today in the Rosemount Emerson space. We'll have a discussion session open afterwards. Oops, there's my slides automatically round back. We will have a discussion session open, so please feel free to type your queries and questions. And then there's a very short survey post at the end of the session as well. So for us to make these a lot more beneficial for you in the future, and obviously to give you all the best benefit, yeah, we'd really seek that feedback from you. That'd be fantastic. Thanks. Good or bad, by the way. Constructive criticism is always good. Hopefully everybody's pretty comfortable with that introduction. I think it's very much self-explanatory. Potable, obviously, it's been around for a number of years. I always used to be quite intrigued where the sites used to be. I must admit, some of the sites I used to visit through the different water boards and the likes over the years were some of the most beautiful sites around, tucked away in places. Pros and cons, obviously, disinfection will be touching base on some of the methodologies, and then we'll look at a quick overview of chlorine and chloramination. Disinfection with the sensor technology as well. So disinfection, for those a little bit green to it all, the main goal is really just to kill any what we call bacteria and the likes. I use the word bugs is my terminology. That says they're pathogenic microorganisms. Basically, you do need microscopes to see a lot of these. Use the word wee beasties. So the common types, obviously, anything from Giardia, E. coli, Scripto, for example. They do get through the system, unfortunately, from a water treatment point of view, and there can be other challenges in your retic system. So as it says there, when microorganisms are not removed from potable water, or could be in the process or other, drinking water will cause people to fall ill, and that's obviously not ideal. It doesn't make good press for a water authority, and unfortunately, as you probably well know, in some cases people have died, de-aged and potentially infirmed. Not well. It can really whack them around, and unfortunately there can be deaths associated with it. Typical disinfection and chlorination overview. Obviously you've got your feedstock. In this particular case it could be a standard reservoir, lake or otherwise. It could be even a river. Then from there obviously there's a pump service. There can be also sometimes a a secondary holding. Maybe you might do some pre-treatment in that particular area, and then the treatment plant. And then chlorine disinfection. We'll touch base obviously on the different styles of chlorine disinfection. I've sort of drawn this just really briefly in a couple of scenarios. Some cases from chlorine disinfection, more cases, it's actually goes directly straight out into the retic system, drawing this sort of partially incorrectly. Or it may also go into what we call a clear water storage facility, where there will be some chlorine residual left behind, but generally there's also another post-dosing after the pumping or the gravity feed into the retic system. Chlorine, just a quick one on the chemistry side of things. I'm not a chemist, but in the same context, I think I've got a fairly good handle on it. Again, the piece is fairly self-explanatory. As it says, the two chemical species formed by chlorine in water in this particular case is hypochlorous acid, as in HOCl, commonly known as, and hypochlorite ion, OCL, some people call it that. And we call that free and available chlorine. So the goal is, through your retic system or your potable water system going out through to your client base, does have a residual, and you need that residual just to eliminate any potential bacteria that are emanating from within your sometimes aged infrastructure and or pipeline facilities. As it says, the weak acid will dissociate according to the formula below. Typically between 6.5 to about 8.5. The reaction is incomplete in both species, and then you have that as a present, as a free available measurement. Hypochlorous acid, as it says there, is the most germicidal of the two, so that's the one that you'd really like to have as a residual, as I say. It's very strong. The upside is it's a very strong, relatively strong, I'd call it very strong, but relatively strong oxidizing agent, as it says there. And then the upside is actually it does react very, very well with a wide range of compounds and pathogens, and is very effective in its kill factor. Particular importance, as it says there, the dissension of the chlorine reaction with nitrogen compounds can be a bit of an issue, such as ammonium nitrates and amino acids, which we'll touch base on as well further down. Disinfection from a chlorination point of view, we saw that previous little bit of a layout picture, but typically from a chlorine aspect, and one of the next slides will touch base on that as well. Chlorine can be injected either in a gas format. That's what I've actually dealt with in the past more so. So typically it's in what we call a ton container, for example. That ton container is in a gaseous format, in a liquid/gaseous format. Usually has a bit of a gas phase on top. Then from there it's vaporized, injected via a ratioed system through like a venturi. You end up with a superchlorinated water, and then that water or that injection is in flow paste against your load, or if you like to call it your flow rate going through to your retic system. That in its own point can be a bit of a challenge in getting that ratio system right, and then more importantly to actually then have a measurement system downstream for that, and then to physically do that chlorine residual measurement. Chlorine, definitely one of the cheapest options and one of the fastest and the most available. Sodium hypo, again very free and available. I believe that's actually a byproduct of chlorine gas manufacture. The upside is, as we suggested before, it definitely has a better kill rate than a primary disinfectant. For example, it has 150 times more potency, so to speak, than monochloroamine. And there has been some papers on it, which I'm not going to touch on today, but it can form, unfortunately, as I say, undesirable byproducts, for example, such as THMs. There has been HAs as well, H-delase as in glycidic acids as well, can also be a byproduct of the reaction. Currently there's been no conclusive evidence, by the way, that drinking chlorinated water causes cancer, for example, and there's some of the rumours out there and or reproductive issues within humans, but definitely large doses of certain DBPs, or if you like THMs and the likes, can and have been cited as causing issues within laboratory animals at this time. The unfortunate part with chlorine, if it's overdosed, I've seen it and smelt it and heard it when I've been out in the rural areas. Unfortunately, it can happen occasionally. What can happen is overdosing. People's clothes, if they're actually washing Washing clothes can actually be slightly bleached with spotting, and you can actually smell it. You can actually get the odour coming through, and obviously tasting as well if the residual is too high. As it suggests there, it loses effectiveness, as in its disinfection demand over longer distances, which can be a bit of a challenge. So over long distance transfer lines, right through to high load systems, for example, typically you have a booster station, and the upside for that is basically you do end up with an increase chlorine residual within your system. The downside is, so obviously you've now got more infrastructure and they're rolling out through in your retic system. Challenges, I think that's pretty much self-explanatory, that picture. It takes the next step from the previous picture. If you probably look at the amount of water treatment plants that are being built, they're not as being augmented, so to speak, with the odd new one. And as you look at, for example, the clients' new housing estates and the likes that are going out, the volume of water being used and some of the distances, for example, because the estates are now moving further and further out into the burbs, so to speak. So the challenge is to now how do you maintain a residual or actually a cure factor in your retic system. So these are some of the challenges that the water boards are currently managing, and with a couple of scenarios that they do have for as we look at other options for disinfection. Ozone's definitely one that I've seen out in the space. Not horribly popular. I've seen them in the wastewater space from a reuse point of view. Fantastic as a primary killer as well for pathogens. We've also seen it in some cases for groundwater. There's a small, beautiful little site down in Port Fairy, from memory. The little water treatment plant down there has a little ozone generator. The unfortunate part, as chlorine gas, if that leaks, is obviously quite hazardous, but you do get a second chance with chlorine gas. Get a big enough dose of it, obviously, it's game over. Ozone, no second chance at all. So from the terminology of being a hazardous area facility or a hazard facility handling ozone, there's a lot of different OH&S aspects right through to HAZOPs. You have to then get your head around in that space from an ozone point of view. But definitely a very good alternative as a primary disinfectant. As it says, it has no taste or colour or odour issues, unlike monochloramine, for example. Doesn't form any THMs. Not overly expensive. You can actually manufacture it on site. You have to freight it in, for example. Nobody makes chlorine, for example, or other. Popular sources, yeah. For the beverage industry, definitely use that. And as it says, the unfortunate part is it doesn't form a residual in the system there. So it requires, for example, chlorine or monochloramine for a secondary disinfection to maintain that residual through the system. Just a little bit of a point, because we've been talking about particular microorganisms, for example, and the likes. Here's just a quick sample of a handful of them there, and here we're just sort of cross-referencing what we call contact. I call it contact time, concentration time for pathogen kill rates, for example. As it says there, 99% log to inactive. So in summary, basically, we're just saying, hey, the pathogens on that retention, on that contact time, or against that concentration, basically, hey, you've got 99.9% logarithmic kill rate. So typically you see T's in what they call milligrams per litre in that particular case. Not much more I can really say in that space. So obviously these are the different elements you do have to look at, and then depending on your application and best fit for your plant and reticulation system, you then choose a disinfection to suit. So as you can see, chlorine, the traditional chlorine, definitely is well used and well respected from its cross-referencing of multiple pathogens. Chloramines, which I didn't talk about on the previous slide, but obviously the chloramination or the chloramine sides of things, which is basically ammonia dosing post-chlorine addition, is really the main purpose for that is to have an ongoing residual for kill rate. So as it says there, ammonia is commonly present in natural waters. will react in hypochlorous or hypochlorite ion form. We're looking for typically a monochloramine. Ideally, you don't want dichloramines or trichloramines. The issues with those basically taste and odour. The last thing you want to do is, for example, have like a chlorophyll smell coming out of your system and the likes. You do get what they call a breakpoint reaction against all those particular activities if you don't physically do your ratioing and your dosing correctly and managing your pH at the right levels as well. Excuse me. Making monochloramine, this is just that little piece that I sort of touched base on just before. So drinking water, aka potable water, so it's already been through the water treatment cycle. Basically, it could be sodium hypo or other. Chlorine gas, typically it's fairly concentrated, and at that point then you have an injection, and then downstream you then inject or add your ammonia. And obviously what we're trying to look for there in this particular case is a monochloramine output that you've got there on the just above the red line. Again, depending on your application, 5 ppm as we're saying, chlorine, excuse me, requires about a 1 ppm ammonia as nitrogen addition. Disinfection options. We've been through a lot of that already, but as it says there, these are some of the pros and cons, for example. Monochloramine is formed, as it says there, by mixing chlorine and ammonia, specific ratio, and ideally you're trying to avoid, as we said, the di or the trichloramines. As it says in that, and we're very aware in these aspects, with monochloramine is not as effective from that previous slide against CT rates as chlorine, but the upside is it does maintain an ongoing and effective longer kill within the distribution system. The upside for chloramination, it doesn't actually create any THMs like chlorine gas or sodium hypo can potentially. And the other upside is actually appears to be very effective in controlling biofilm, which can be a bit of a problem depending on the age of the network, for example, and the style of network that you're currently running. Traditionally doesn't have taste and odour problems. You can be concerned about nitrification and health concerns around that particular space. As it says there, it's a key aspect for chloramination, and ammonia dosing is really looking for that free ammonia in the system, just to pick up any particular issues in potential nitrification, which we'll also touch on in the measurement aspect shortly. Sensor technology, I'll shoot through this fairly quickly because I'm just looking at the time and I'm hideously late sometimes, and can get a little bit long in the tooth. So amperometry in this particular case, as it says, is detection of ions basically in solution base. For the want of a better word, there's an ion exchange through an interface membrane. As it says there, you can get different styles of membranes depending on the technology of the ion, because it is ion selective. And we also do change the fill behind the membrane technology, depending on the application as well and the particular ions we're trying to look for. This is I've covered most of the points. One of the highlights, I think, of this technology, though, obviously, is it's reagent free. So there's a fairly minimal cost of ownership with these sort of styles of devices, getting back to the previous points we made at the start. So there's no ongoing reagents and the likes. You do have to change the cap fill. Typically that's within, depending on the application, rule of thumb and the activities that I've been involved with over the last few years with the Emerson team, about every 3 months. We tend to get a really good life cycle out of those cap membranes and the fill solutions. And the upside with these sort of spaces, a lot more easily rolled out in this sort of style of technology. Pre-assembled sample panels, as it says there. We'll touch base on that a little bit further down as well. I think I might have shot through to no, I do apologies. Just a quick overview. We've sort of touched base on this. This is a little bit of an example for an O2 that's shown in this particular case. Just a quick snapshot as an overview. As it says, basically you get in this particular case O2 of the analyte is what's commonly known as. passes through the membrane, which is typically selective, and then reacts with a cathode nanode/electrolyte. Generally, the electrolyte can be KCl, but we do actually manufacture and change the electrolyte depending on the application, which we'll talk about shortly in the case of, for example, free chlorine. That's just a little bit of an overview. So the only real, if you like to call it, maintenance aspects may be the actual anode-cathode arrangement, and definitely you have to do changes on the electrolyte. This is a little bit of an example of some of the changes that that technology that we've been talking about, the ampermetric series. Typically, it's quite challenging from a pH point of view. You can get compensation or measurement issues depending on the ions you're physically trying to measure. We have several ways to work around that. In this particular case, the graph or the layout on the right just shows what we have with regards to a fill solution that we have in our particular free chlorine sensing system. I suppose in summary, it has a highly buffered acidic solution, and in essence it pre-adjusts the pH adjustment prior to any ions coming through the electrode measurement system. The graph on the left just shows some of the potential changes you can get on pH versus physical measurement. So with the systems that we have from the ampermetric aspect, for example, you can get less than 4% unit change in a pH between 6.5 and up to about 10. And below 6.5, as you're probably well aware, the change is quite minimalistic. Some people can and have used also ORP in that space for measuring chlorine residuals, but you do have to have a very set and firm pH within your potable water system. Generally, I see more of those applications of things like cooling towers, for example, or chlorine residual aspect. As an alternative, we also do pH corrections, by the way. One of the next slides will be touching base on that for free chlorine. And that's typically, again, depending on, if you like to call it, your comfort levels with regards to adjustment changes and or physically entering a particular nominated pH of your system, and or how much your process system changes in pH. So we can actually actively measure and manage that accordingly. We can actually go from down to 6 pH up to 9.5. And we have also got systems out there running currently at 10 pH. Not common, obviously, though, in necessarily retic systems. A little bit of a summary going over the membrane. Obviously, it defines a diffusion zone. Obviously, that's what the membrane does, is selective otherwise. One of the key elements in that, obviously, the membrane can also help reduce interferences. I see those are very key. Hydrophobic membranes obviously tend to block ions and molecules dissolved in water. For example, they're only permeable, and they're what we use, for example, in our case, for total chlorine, if we're using like an iodine system, ozone, or oxygen, depending on what sort of style of system we're actually using. Hydrophilic membranes, as it says there, permeable to dissolving water and less ion selective, basically. In our particular case, we use those for free chlorine and monochlorine measurements. As it says there, permeability of the membrane is affected by temperature, not dissimilar to pH. The impedance does change, and it doesn't really help in that case when the temperatures are quite cold, and not uncommon to have obviously cold temps. Just a little bit of a snapshot looking at some of our systems and solutions that are currently available today in the marketplace. This is just a little bit of a quick overview of a system. In this particular sample, we're looking at a free chlorine system with pH compensation. What we have there, in this particular case, is a pH, obviously a measurement. That's multitask within, we have a 1056 or a 56 series. I won't go into the detail on that. Definitely hit our website if you want more detail on that. And then from there, we obviously have a free chlorine measuring electrode, ampermetric, of course. And one of the things we do pride ourselves on is what we call a constant head flow controller. One of the key reasons for that little system on the far left is that it maintains the constant head. With a constant head, you end up with a constant flow. So unfortunately, as you know, with reticulation systems at night, for example, the pressures increase. During the day, during load, the pressures drop off. And if you're not regulating that very clearly through to your analyzer system, you will have flow rates which will change in and out of your measurement system. With changing flow rates, you'll actually end up with changing measurements, unfortunately. We'll absorb that, if that makes sense, those changing flow rates from a regulation point of view, and run it through what we call a constant head flow regulator. So anything excess from a pressure will actually then overflow and run through to waste, for example, or back through the system. Monochlorine system, same sort of similar style of outlay again, from a layout aspect. You've obviously got a monochlorine system. In this particular case, it's actually a chlorine cell. So quote unquote, we're actually measuring 0 to 6 ppm as chlorine in the monochlorine space. With every one we do supply in the monochlorine or the chlorine space, I forgot to mention, you actually get a membrane kit, 3 of them, so it'll last based on sort of a 3-month sort of upgrade if you were having major issues with membranes. Generally, you don't always replace the membranes. It's just physically topping up the electrolytes and the likes, and you also get a bottle of electrolyte. I do like that as a function. It's quite you're ready to rock and roll when you receive the unit. And as I say, when you're looking at monochloramine, when we're talking about look for the measurement of free ammonia, for any particular issues downstream when you're doing monochloramines, for example. We also do a system that measures total ammonia, and we can dovetail different systems to suit depending on your application. So we can do anything from a total ammonia system, along with monochloramine coupled together, along with pH. So again, so we can sort of tailor systems and applications depending on what your process and your application requires. Again, from left to right, constant flow controller. We really embrace that technology. I won't say technology, it's fairly basic, but it works really, really well. For our ammonia, so we have what we call a solid state electrode in that space, and then amplimetric, obviously, for your monochlorine. As you know, ammonia overdosing can lead to nitrification, as we discussed before within the system. And the keys are really to, I suppose, optimise the initial dose of that measurement for monochlorine, and then to gain that free residual of ammonia that we'd like to measure and keep really tap on. So you will potentially have some free ammonia, but you don't want to have overdosing of ammonia. What I do like about this system is no particular reagents and no real cost of ownership. So it's quite a unique and simple little system. That last point, I suppose, just talks about no need for pH correction unless the pH fluctuates. Not uncommon for pH to fluctuate, and for myself to have a belts and braces approach. I definitely request 9 times out of 10, depending on, again, the pH fluctuation, but it generates a good aspect to have pH compensation on it as well. So I suppose that just really segues into some of the other disinfection and water treatment solutions we have in our portfolio. Basically, it's a modular system, and we can manufacture and set up a system that will suit your application and your purpose for chlorine measurement, monochlorine measurement, nitrate measurement, for example, or residual ammonia. You do want to keep an eye on in your system if you're dosing using a monochlorine system, for example. Just talking about some of the events we do have coming up in Brisbane. We're actually doing an Emerson Events rollout show, so to speak, where we have key speakers and hardware and field devices and topics. It's quite an interactive session. The next one's coming up in Brisbane on the 28th of August. We've got one in Melbourne on the 30th of August, and Friday the 1st of September in Perth. There's a link there. Please, if you get a moment, scribble that down. Usually it's very interactive and quite interesting with some particular topics, and you'll be able to get some more information off that site. Thanks again for your time. Apologies for running a little bit over time, as I sort of rushed a little bit more towards the end of the bit as well. if you've got any particular questions and queries, please let me know. What we'll do, I'll open up the little questions to the chat area. If there's any particular queries and questions here, please feel free to ask. I'll just sit here and hang online for a little bit. And alternatively, what I can do as well, if we don't have any particular queries and questions, I'll set up the survey for you, and yeah, if you'd be able to give us some feedback, that'd be fantastic as well. I'll roll that out. So I think the survey is fairly self-explanatory, but yeah, really for us to better a lot of our discussion points, please feel free to give us some feedback, again, positive or negative. We find it very invaluable, I must admit. Thanks very much for your time. Take care. Yeah. Bye for now. So sorry, Elton. Thank you. Cheers. Thanks, Elton.